In our previous video, we have seen how diamagnetism occurs in normal materials, and we described a small experiment to see whether the item or the material is diamagnetic, paramagnetic, or ferromagnetic. And in that experiment, the uh, crucial thing was to note that uh, the material which we are going to hang should be symmetric so that there is no unwanted unbalanced motion. And finally, we should always be able to measure the final displacement from the original position once after all the oscillations or disturbances have died out. So uh, if that displacement is towards the higher field, then it implies that it is either paramagnetic or ferromagnetic depending on the force or the displacement, how much it is there. And if it is away from the higher density of the field, then it means it will be diamagnetic. Then I told that diamagnetism is shown by every material, it is an inherent property, but it is overwhelmed by either paramagnetism or ferromagnetism in many of the materials. Now, as I have told that the magnetization is in a direction which is opposite to the applied or the field. So based on the expression that this magnetization is proportional to the h, then I can write that this chi, the proportional constant, is negative here because the direction is opposite. So we can say that this proportional constant is smaller than 0 for diamagnetic materials. Since this effect is very small, so its value is around minus 1.00 something. That is, the effect is very small and it shows that proportionality is still there, but the direction is opposite, and this effect is very small comparatively. Now, in this lecture, we will see what is the cause of paramagnetism in the materials. Now, there are some permanent magnetic moments in materials, although they are randomly oriented. But and because of this random orientation, the resultant magnetization in the material is zero. However, there are still permanent magnet moments which are present in the material. But when we place them in an applied field, these permanent magnetic moments they get aligned along with the applied field, and because of this they show attraction towards the higher density field. Because of alignment, uh, they feel a force of attraction then. But similar to the strength, if we compare to diamagnetic materials, the strength of this action is again weak, only similar to the other phenomena which we have seen. So paramagnetism is also a weak phenomena, and this lining up of forces are very small compared to the thermal motions which are present in the material. Like you see, because of temperature, the thermal because of this temperature, the electrons or the molecules and atoms, they are always in some kind of vibration jiggling like this. So those thermal vibrations are much more stronger as compared to this lining up action of the magnetic moments. So it implies that this effect of paramagnetism is sensitive to temperature. It implies sensitive to temperature. That is, the alignment of the moments along the field is can be easily broken or overcome by the thermal motion of those constituent particles. So because of this, we can see that if temperature is increased, then the paramagnetic effect is reduced. Or we can say, if temperature is reduced, then we will find that the effect of paramagnetism is little more seen, or it is little stronger. Now this effect of paramagnetism can be explained by, the precession of the magnetic moments when we apply an external field uh, on the material. So by classical theory, we know that electrons are rotating with the orbital motion as well as the spin motion, so they have an angular momentum. So when we apply a field, they have some kind of torque because of that applied field. Now since they are already in angular motion, so they have already some angular momentum. So because of this torque of the applied field, there is a change in momentum, and there is a precession which we might have studied in our 11th class during rotational motion. So that this effect of paramagnetism can be explained by using that concept also, although we are not going to delve further into it. Now, according to quantum mechanics theory, whenever a magnetic material is placed in an external field, then its energy changes, and the energy splits into definite levels. Like an electron, when it is placed in an external field, it can have two energy levels only, with its angular momentum number given by some quantity half h cross and minus half h cross. So although this we will not go into further details, but if you are interested, then I can refer you to the Feynman lectures on physics for further detail. And the concept is very beautiful and simple to understand as far as those lectures are concerned. So but for like our electrical engineers, it is not much required. We can just explain these effects because of the classical theory only. Now the question comes, what kind of atoms have magnetic moment? So any atom like sodium, where they have an odd number of electrons, they will usually have a magnetic moment. Similarly, some ions, they can have magnetic moments. Like in sodium, it has one electron in its unfilled shell, which gives the atom both a spin as well as orbital magnetic moment. And in general, compounds are usually not found to have those kind of magnetic moments because their valence electrons are filled with each other by satisfying valence conditions, and the electron spins are balanced. Thus in general, molecules do not have a magnetic moment, but there are some materials like O2 molecule, it can have magnetic moment, and its explanation can be given in some chemistry class. But there are so many materials which have unfilled shells, and the electron is not paired, so because of that it has that magnetic moment. Now it can be proved that paramagnetism, in paramagnetic materials, the magnetic moment, it's proportional to tangent hyperbolic b by t. This is the Boltzmann's constant. So if I plot this, we will find this kind of curve. You see, so in paramagnetism also this saturation occurs, but we are not able to see the saturation because at normal temperature it is not easily seen. So we, to see this effect, we will have to go below a certain temperature, and only then we will be able to see this saturation effect. Otherwise, when this thermal motion sets in, it will just break those lining above the moments, and we will not be able to see this saturation, which implies that all the magnetic moments have lined up, and no more further increase in B will cause increase in M. But this effect is rarely seen at room temperature. No, now if B is equal to 1 Tesla and temperature is some few fraction of a Kelvin, only then we will be able to see this. So practically for all materials, we are not able to see this saturation in paramagnetic materials. Now there is a very interesting application of paramagnetism which we can use for cooling of the materials below a certain temperature. So what is that? That is cooling by adiabatic demagnetization. So let us say that we have a paramagnetic material and we have cooled it using some, let us say, liquid helium up to a certain temperature of that liquid helium. Now we want to further reduce the temperature of that paramagnetic material. So how to do that? So what we will do, we will cool down such material until the saturation in paramagnetism is seen. So we will cool down, reduce the temperature till saturation is seen. Then we will slowly remove the field which has created the saturation. We don't have to remove the field fast. We should remove this field slowly. Otherwise, we will not be able to see this adiabatic demagnetization. So that thermal motion has to do work against field to flip the momentum, the magnetic moments. So when we will gradually remove this field, then the thermal motion of the particles will have to work against this field which is gradually changing, and so in that they will have to work, and that work will be although help in flipping the moments, creating demagnetization, but this demagnetization has taken their energy, so they will further cool down. So you see that by demagnetization beyond a certain temperature, we can again get further reduced temperature by this adiabatic demagnetization of paramagnetic materials. Now you see, this thing is happening because of the majorly spin moments of those electrons. Now there is moment of nucleus also. Now if we want to further reduce the temperature, then we can use the similar effect for the moments because of the nucleus, which although which is very small, but it has been done. And the second level of reduction in temperature is done through the adiabatic demagnetization of the nuclear moments because of the nucleus. So in this way we can have two stage of cooling: first of electronic moment and second of the nuclear moment. So I believe this application you might not have seen in electrical engineer or in engineering, although it is fairly known to physicists. So this is one of the applications in which we are using the effect of paramagnetism to get reduced temperatures. So I believe I have explained the basic reason of paramagnetism. It is because of the spin moments of unbalanced electrons which whose spins are not balanced, that is the atoms which are having odd number of electrons in their shell. Now in the next lecture we will see how this ferromagnetism occurs, and briefly we will see some other effects, ferrimagnetism or anti-ferromagnetism also, and we will try to explain those effects in terms of domain wall theory as well as the magnetic moments theory because of the spin, and the interaction energy, which is going to be explained by just quantum mechanics only. There is no explanation in the classical theory, but we will not delve into deep quantum mechanics. We will just touch upon it. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group, whose link is given in the description of this video. Thank you.